on is I'm going to go over some problems. I have a bunch of problems on an assortment of topics that we're going to go over. If you have any specific, I'm going to make a judgment on each problem about how much I need to review or what I should talk about. But if you guys are confused about something like a definition, I just ask me and we can go over it. I'm happy to do that. Yeah. Yeah. So I have a couple problems that on various topics related to the exam, and on those problems, they're going to use some definitions we know, or like some facts about things we know. And if I've assumed something that you have a question about, feel free to ask a question. Okay, so first we're just going to review some terminology. And so these are just a bunch of different words having to do with proofs, theorems, stuff like that, that you should know the definitions and roughly what they correspond to. So the first one is an axiom. What's an axiom? Well, in mathematics, when we're doing proofs, we always have to give reasons for why we can go from one step to the next step. Axioms are, at the end of the day, what you can justify from going from one step to another step. So these are, we can't give proofs for everything. At some point we have to say, okay, this is true, and the axioms are the things in our system that we say, okay, these are the facts that are true and don't need to be proven. Let's see. Then we have theorems. These are statements that we prove true. Among theorems are generally, you use the word theorem for like the big statement that you prove. Along the way you can have these things called lemmas. And lemmas are kind of smaller results you use on the way to proving your big theorem. So you see the word lemmas, it relates to theorems like that. And another word you should know is corollary. Sometimes when you prove a big theorem, as a consequence of the big theorem, you have some other results which follow essentially from the theorem, and we call those corollaries. All right. In mathematics, we're concerned with proving propositions. You should know from propositional logic that a proposition is some declarative sentence that either has to be true or false. All right, so those are just some basic terminology about proving things and our statements that the professors like to do. Okay, now we're going to do a quick review of De Morgan's law problem. And this problem is going to be simplify not P or Q, and so with De Morgan's formula, and our goal is to pull all the not signs in so that there's not signs only precede propositional variables. So what do we do here? Well, we apply De Morgan's formula. We say the not of this and this is the same as the not of this thing on the left or the not of this thing on the right. So we get P or Q or not R. And then everything comes out nice. Yeah.
Can you write a little bigger?
Yeah.
Thank you.
And then all we did was to say the not of something and something else is the not of the first thing or not of the second thing. So we got Q or not. Yeah.
For the peer Q part, it is canceled if you not.
Yeah, so not of not is. And you should also realize that De Morgan's formula also applies to sets. So in set language, what we've just done is we've taken the statement S union T complement intersect R complement, and we've simplified that down. Yeah.
So that's in which language, sorry? Like just
So De Morgan's law has a version that has to do with propositional statements. There's also you can also use De Morgan's law when looking at complements of sets, because complements are kind of like not in this set. So you saw a version of De Morgan's law for propositional logic, which looks like this, and you've also seen De Morgan's law for sets. Yeah.
Can you show what just the inner knot does? Is that the same?
Yeah, okay. So if you were just to apply De Morgan's law here, where if you just put a knot in front of the thing on the left and a knot in front of the thing on the right, what you're going to get is like a knot, and then in parentheses, another knot of this. Does that make sense?
Like, can you do the inner, like the knot P and Q? No, not P or Q.
Oh, okay, you're
Yeah,
saying
you like the inner one? And then,
you want to do this first?
yeah, just that knot.
Okay. So then we'll get knot of knot P and knot Q and R. Can you see this? Is this too small?
I can see it.
And then you do the same thing as you did before. You're going to pull in the knot into the thing on the left. So that's going to be knot of knot P and knot Q, or knot R. And then you do it again over here. You get P or Q or not R. Is that what I got over there? P or Q or not R. Good? Any more questions on this? And good exercise is try and do the same exact thing, except do it in terms of sets and complements. And it should be the exact same procedure. All right. Next problem I want to review is on relations and equivalence relations. Did someone say that? On relations and equivalence relations.
So when you have the line on top for the sets, that means like that whole thing is not, right?
Yeah, so this knot, or this complement is kind of over this entire parentheses.
Okay.
So take the set which is defined by what's inside the parentheses. Sometimes you might also see complement denoted by like a little complement sign above the parentheses. Various notations. Yeah.
so the bar means complement. Is that what it means?
Yeah, the bar just means complement. So, yeah, bar means complement, which just means take the set below the bar and get the set that's defined by everything not in that set. Okay, equivalence relations. Yes.
Do you actually have like a quick example you could do the one relations with Morgan's? Because I actually have more trouble.
With the sets?
Yeah.
Okay, yeah, sure. We could do this one in terms of set language, and let's do it by doing this first inner one first. So we'll keep the big parentheses in the bar. I'm going to simplify this one first, and within that one, I'm going to have the complement of S union T. So that, by De Morgan's law, is going to simplify to S complement intersect T complement intersect R. Now let's use De Morgan's law to take this complement on top and bring it inside. Okay, so we're going to get the complement of the thing on the left union the complement of the thing on the right. And now we simplify this guy. That guy is going to be complement of the thing on the left. Flip this to union complement thing on the right. So we're going to get S union T. And then union R complement. Does that help? And you can see this is essentially exactly what's happening over there. Okay, equivalence relations. So I'm going to define a relation. Define relation R on the natural numbers greater than or equal to 1. I'm gonna say that the natural numbers here start at 1. Some people start at 0. For this case, these sets are greater than or equal to 1. So I'm going to define the relation R on this set by, and everybody knows what this set is, right? This is the Cartesian product. Anybody not know the Cartesian product? Okay, good. Okay, so the elements of this set are going to look like A comma B, where both of these are natural numbers greater than or equal to 1. So I'm going to say A comma B relates to C comma D when AD is equal to BC. Okay, and the question is, prove this is an equivalence relation. Okay, to prove something is an equivalence relation, you have to show 3 things. You need to show it's reflexive. You need to show it's symmetric. And you need to show it's transitive. Okay, let's start off with the reflexive part. So, does A comma B relate to A comma B? This is kind of like a relate question part, because we don't know it yet. So, if we took this rule, which basically says, does the first element in the first tuple times the last element in the second tuple equal the middle elements, we'd get that A times B is equal to A times B. So in fact, these two things do relate to each other. So I wanted to see if A comma B relates to A comma B, so I multiplied the first element with the last element, and then the two middle elements, they're equal to each other, so it does in fact relate. Okay, yeah.
The order doesn't matter, right? So like AB equals BA.
Yes, because these are natural numbers. When you multiply natural numbers, it can be used. Yes?
Can you just remind me what the rule for reflexive is? What is it?
Yeah, so we say a relation is a reflexive. Let me just put it up here. We say a relation R on a set S is reflexive if, for all elements of the set, that element relates to itself. So the relation says, give me any pair of elements, I'm going to tell you either good or bad. And the relation is true when it's good, or it's bad when it's false. And let me just finish this. And all reflexive says is that whenever you take the same element, the pair of that same element is good. Is part of the relation. Yeah.
What does it say after if? I'm sorry, I just can't.
Yeah. After what?
After if, reflexive if, for all S.
Okay, we say a relation R on a set S is reflexive if, for all elements of the set S, we have that S relates to S. Little s relates to little s. So every element relates to itself. Okay, cool. Okay, next we need to check if this relation is symmetric. Recall a relation is symmetric if A relates to B, oh, I guess I shouldn't say A and B. If an element, if any pair of elements that relate to each other in the opposite direction. Okay. Let's give me a little bit more space. So, suppose A comma B relates to C comma D. So we're trying to prove this implication. So let's assume that these two things relate to each other. Then we know that AD is equal to BC. Okay. We want to show that C comma D relates to A comma B, which is true when first and last element, CB, is equal to AD. So since we know AD is equal to BC, we also know that CB is equal to AD. So we said we want to prove it's symmetric. Suppose that these two things relate to each other, then we have AD is equal to BC. But the requirement for the reverse pair of them being related to each other is just the same equality in reverse. So we get that. The former implies the latter. Make sense? Yeah.
Can we go over antisymmetry?
Yeah, sure. So we say two things are we say R is anti-symmetric if A relates to anytime, okay, I'll call these E1 and E2. If anytime two things relate to each other and their kind of swap relates to each other, those two things, I'll just say implies here. Those two things are equal. So symmetric says whenever two things are related, their swap is related. Antisymmetric says the only time that you have two things that are related and their swap being related is if they were actually the same thing. So a good example is equality is antisymmetric. The only time that, well, I guess equality is kind of a silly example. You don't get
Basically, you can say that every time E1 and E2 are related, you cannot find their swaps being related.
yeah, sure. Yeah. And so anytime you, equivalent, you can say, anytime you have two different elements, you can't have both they relate to each other and their swap relates to each other. Does that answer your question? Okay, so we need to prove that this is an equivalence relation. Equivalence relation has three parts: reflexive, symmetric, and transitive. Does not require antisymmetric. And so the last thing we need to check is that R is transitive. Transitivity. Okay, suppose A comma B relates to C comma D, and C comma D relates to E comma F. So suppose we have two pairs of things, or some element relates to some other element, and that element relates to another third element. Okay, we need to show that this first one and this last one are also related to each other. And we show that, what do we need for these two things to be related to each other? We need to show that AF is equal to BE. Okay, so we're trying to show that AF is equal to BE. Okay, so well, what do we know? We know that AD is equal to BC because these pair of elements are related. And we know that CF is equal to DE. Okay, so now we kind of have to stare at this a little bit, because ultimately what we want to show is that this equality, and we want to get this equality from these two equalities. So what I'm going to do is I'm going to multiply by B. I'll multiply by B. Yes. Well, okay. All right, BCF, I'm going to multiply both sides of this last equation by B. I'm going to say BCF is equal to BDE. Well then, since we have BCF on this side, and we know that BC is equal to AD, we're going to get that ADF is equal to BDE. And now these D's cancel, and we get that AF is equal to B. Any questions? So I should say, how you get from these two equalities to this last equality requires a little bit of thought. And you probably have to stare at it for much longer than I took to stare at it, because I've seen it. But on the test, you won't have to. It won't be something that you have to stare at for that long. So if your questions about that, then I wouldn't worry about it so much. Yeah.
Can you just kind of one more time explain those two, how you got to those three statements?
Yeah, sure. So we knew that these two elements are related and these two elements are related. Because these two elements are related, we got this equality, and from this we got that equality. Now I want to go from this pair of equalities to AF is equal to BE. Okay. Well, this has an F in it, but it doesn't have an A in it on the left-hand side. So suppose I want to get an A in it on the left-hand side. Well, one way to do it was just multiply through by A, but another way to do it is if I multiply by B, then I'll get a BC on this side, and if I have a BC on this side, that also brings in an A. So maybe let's try that. Perfectly valid move, multiply through by B, right? So now I multiply both sides by B. Now I have a BE on this side, which I would like, but there's a D hanging around. I'm just going to ignore that for a second, and I'm going to look at the left-hand side. BCF. Okay, well, this isn't what I'd like it to be. I'd like it to be A, but I do know something about BC. I know that BC is equal to AD. Okay, so let's just plug that in. I'm going to get that I'm just going to replace BC by AD. So then I get ADF on the left-hand side, and I'm going to get BDE on the right-hand side. Now I have a D on both sides. I cancel both of them, and I get the equality I want. Yeah.
Where did you pull CF equals D from?
I'm sorry?
Where did you get CF equals D?
Where did I get CF equals DE? This one, right?
Because you got AD equals BC from the transitive flexor function, right?
No.
Oh, I mean, no.
So
I meant for the symmetric one.
No. So I got it from, when you're showing something's transitive, you have to show that whenever one element relates to another, and that same element, that same last element, relates to a third thing, implies that the first and the last are related. E1 relates to E3. So this is the property of being transitive, right? Yes?
Yeah.
So in order to show something's transitive, I assume that I have some E1, E2, and E3 where this first property holds. And in that case, that means I have a pair A comma B relating to a pair of C comma D, and a C comma D relating to an E comma F. So I'm given these, and I'm trying to prove this last one. So, but by the fact that I'm given these, I can use the definition of the relation R, which is, we say that two things are related to each other when AD is equal to BC.
Okay, I just didn't see it.
Oh, okay, yeah, sure. So does that make sense?
Yeah.
On like the exam, would we obviously be, like a problem like this, we would be given AF equals BE, show us how to find this. We wouldn't just kind of have to, because I feel like without that statement, we'd be kind of not knowing what we're aiming for.
Well, you know you have to aim for this, right?
Yes.
And the definition, how you show that one thing is related to another is by, so yeah, does it make sense?
Yeah, it's just, you kind of wrote it out, which is why.
Yeah.
Okay.
I just want to make it clear so that, good. Any other questions? Okay, one other thing you should know how to do with equivalence relations besides just proving something is an equivalence relation is, well, there are two things related to equivalence relations that are important. One is that equivalence relations are the same as partitions. I've decided not to do a problem on that. And another thing you should know about equivalence relations is equivalence classes. So equivalence classes is, well, okay, whenever you have an equivalence relation, you can define an equivalence class which is made up of all the elements which relates to one specific element. So if I pick any element, what do I want to erase? I want to erase this. So if I pick any element in the set, I can talk about its equivalence class, which is denoted like this. So I'm just going to pick one specific element from the set, 1, 1, and I can talk about its equivalence class, which is usually denoted in brackets, which is the set of all things, all A comma B, such that this specific element relates to that element. Okay, in this case, what is the equivalence class of 1, 1? Let's compute it. So for an element to be in the equivalence class of 1, 1, it needs to be related to 1, 1. So we would need to have that 1 times B is equal to 1 times A. So A equals B. And so the equivalence class of 1, 1 is just the set of pairs K, K, such that, or maybe I'll call this A, A, such that A is a natural number greater than or equal to 1. Does anybody recognize what this relation is doing? Or does anybody recognize where you've seen this relation before? You've all seen this relation. It's actually very important to a lot of mathematics that you do. Not determinate. What? It's not discriminant. Think simpler. So, let me give you a hint. Think about fractions. When are two fractions equal to each other? Yeah, so we say a fraction, A over B, is equal to C over D when AD is equal to BC. So this is actually how we define fractions. We say take this Cartesian set, look at the equivalence classes of that Cartesian product under this equivalence relation, and whenever you see a fraction, with a fraction like is an equivalence class in some sense. But that's just something to think about. But you won't need to know that for your exam.
That says A comma A, right? After.
Yes. So the equivalence class of 1, 1 is all pairs of natural numbers such that the first thing is the same as the second thing.
And we just use A's to denote that.
Yeah, I just used A's in this case, but you could pick anything. Oh, did someone say something? Yeah.
So wait, for our proof for symmetry here,
Yes.
would that also be the same proof for anti-symmetry? I mean, I know it wouldn't affect that it's an equivalence relation, but wouldn't it have to be the same thing?
No. It would be very different.
Because you're still saying that you're still at the end of the day getting back to the fact that they're equal to each other no matter what.
I see. So, in symmetry, you're trying to show for all elements of your set, they are related if and only if their swap is related. So that's saying this kind of symmetry property holds for all the elements. In anti-symmetry, you're saying that symmetry property only holds whenever that pair is the same element. So they're actually very different. You can't be in equivalence relation and be anti-symmetric unless you only have one element in your set, because they're contradictory. Well, for any non-silly equivalence relation, you can't be both symmetric and anti-symmetric. What we proved was that in our symmetry proof is that whenever this holds, we get an equality about something. We get something equals something, and that equality is symmetric, and therefore we get this. So when this equality is different from that equality, I think you're confusing these two equalities.
Because if you're saying that AD is equal to BC, then
Okay, that's this equality.
so can you just rewrite AD as X and BC as Y? X is related to Y, Y is related to X, X is equal to Y no matter what. It's anti-
Sure, AD is equal to BC, right? But that doesn't mean that this element is a pair, it's a different object altogether.
Okay.
You see what I'm saying?
Yeah, I get what you're saying.
So the product is the same, but as a pair, they're different.
Oh, that was okay. Fine.
Yeah.
Well, when you were talking about the equivalent set, so the reason you wrote A comma A is because A equals to B?
Yep.
That's right. Okay.